Alright, we're up and running. Okay, so today's topic is 3D geometry. So you guys should open the handout that I posted in the Google Classroom, and then we'll jump right in. So the key to 3D geometry is figuring out how to convert a 3D problem into a 2D problem that you can draw on paper. Right. Yes, this is the... Okay. So, we want to convert a 3D problem into a 2D problem. So if we look at the first problem, right, it says... Alright, so we start with a right prism with height h, has bases that are regular hexagons with a side length of 12. A vertex A of the prism and its three adjacent vertices are the vertices of a triangular pyramid, and the dihedral angle, the angle between two planes, formed by the face of the pyramid that lies in the base of the plane, and the face of the pyramid that does not contain A measures 60 degrees. So the key to any geometry problem is obviously, we start off with drawing a good diagram. So the way it's described, we have a right prism with regular hexagons for bases. So that looks something like this. Right, we have a regular hexagon, and then a regular hexagon on the bottom. And it's a good idea to draw edges that are there, but you can't see them as dashed lines. To help maintain perspective. Alright, so we have this. And then a vertex A of the prism and its three adjacent vertices are vertices of a triangular pyramid. So if we choose this vertex, the vertex right in front of us, to be A, its three adjacent vertices are vertices of a triangular pyramid. And even if it's not explicitly stated in the molecule, it's a good idea to name them. So BCD. And we're told that the dihedral angle between face ACD and face BCD is 60 degrees. So what exactly does that mean, right? It obviously means the angle between the plane is 60 degrees, but does that necessarily mean that angle ACB is 60 degrees? No, because this angle could be any angle, right? So which angle is equal to the dihedral angle? One property of the dihedral angle is if you draw altitudes to the line where the planes meet, so the planes ACD and BCD meet at line CD, right? So if you draw the altitude to line CD from A, and you draw the altitude to line CD from B, right? Technically that's a line that you can't see, but if we call this point E, then angle AEB will equal 60 degrees. And note that this point isn't necessarily, right, the only reason these altitudes meet at the same point is because BC equals DC, or BC equals BD, so the altitude from B is the midpoint of CD, and same with AC equals AD, so the altitude from A is the midpoint of CD. So the only reason they meet in the same point is because they're isosceles triangles. So this is not necessarily true in all circumstances. But in this case, this is true. And because these are both perpendicular to this line, this relationship will hold. The angle AEB is equal to the dihedral angle, 60 degrees. Okay. So now we're asked to find the height of the pyramid, given that the side length of the regular hexagons is 12. So how might we use this? So, every 3D geometry problem is essentially a 2D geometry problem, or one or more 2D geometry problems hidden among a 3D shape. Usually there's about 2 or 3 2D geometry problems. You can put them together, and that will give you the 3D shape. So here, what we're trying to find is H. So if we only consider this pyramid, we're trying to find H, which is AB. Now we're given that angle AEB is 60 degrees, so it makes sense to look at the 2D cross section of that triangle. And so this is AEB. We know that this is 90 because it's a right prism. This is 60, and this is obviously 30, and this is H. Okay, and then if we look at now, it makes sense to look at ACD, triangle ACD as well, because we know two of the sides in triangle ACD, and we also know the angle. So this is A, this is C, this is D. These are each 12, and we know that E lies here. So now, and we also know that this is 120 degrees, right? Because this is a triangle, or angle CAD is a vertex of a regular hexagon. So now we can go about finding some more information, right? We know that length CD is 12 root 3, so CE is 6 root 3, and ED is 6 root 3. And then that also gives us that EA is 6. And if EA here is 6, that means EA here is also 6. And so if EA here is 6, then here H must equal then 6 root 3. Alright, so it's more about the difficulty in 3D geometry lies in figuring out how to put a bunch of 2D problems together to create one 3D problem. Alright, are there any questions here for the first question? Okay, so let's look at question 2 then. So this was pretty straightforward because we were dealing with straight lines and regular shapes that we know. But what about other shapes, such as the more complex shapes, which are cones and cylinders? So in problem 2, we have two congruent right circular cones, each with a base radius 3 and height 8, have the axes of symmetry that intersect at right angles at a point in the interior of the cones, a distance 3 from the base. Now we want to find the maximum size of a sphere that can fit inside both cones. So as with always, we start off with drawing a good diagram. So if we draw a single cone, so it looks something like we have the base, and then its axis of symmetry is something like this. And we're told that the axis of symmetry of the other cone is 3 inches up, and it intersects perpendicular. So this is the axis of symmetry of the other cone. And we're told at this point, so if we call this A, if we call this point A, the base of the center of the other cone, so we'll call this B, is the center of the first cone. The center of the other cone is 3 inches away from A. So if we say that it's right here, C, and then we draw a perpendicular circle, one thing to notice is that if we draw the radius BD parallel to AC, this length is 3, this length is 3, this length is 3, and obviously then CD is also 3 because it's a square. So if we draw a circle right here representing the base of the cone, it's tangent to the other circle at D, but they are in perpendicular planes. Okay, so now we have a very complex 3D picture. So how do we convert this into a 2D picture? Well, we want to find a sphere that fits inside this middle region. So it makes sense to, if we take a 2D slice of the middle region. So a 2D slice like that, a plane that parallel to this that I just drew, down the axis of symmetry of both cones. And so we'll get, so it's all about converting a 3D problem into a 2D problem. So we have, this is point B, this is point D, we have point A, alright, hold on, I'll redraw it. Okay. So we have point B, D, A, which is 3 units up. And then we have C right here. And so the other cone the projection of the other cone will be like that. Right, there we go. And so we have a central figure, which is this square right here. So how do we now use this information? So first off, the sphere that fits inside, it's equivalent to a circle. And we want the largest possible circle, which means it should be tangent to all 4 sides. Right? So we have a circle somewhere there. Right. So we have a circle somewhere there. And it's tangent to all 4 sides. Okay. So what can we do with this? Well, if we draw a perpendicular right there, so hold on. If we notice that this A must be the center of the circle, because the angle bisectors. So A must be the if we look at this quadrilateral that's formed by the intersection of the triangles, we'll call this D, E, F, G. A must be at the intersection of the circles, and so A must be the intersection of the angle bisectors, even though it's poorly drawn here. And so if we draw this perpendicular right here, that should be our point of tangency. And so all we need to do now is figure out the length of H right here. We'll call that. So all we need to do now is figure out the length of H. So if we notice that there's a pair of similar triangles here, if we extend CA all the way down to the end, there's a pair of similar triangles. we'll call this AHI, and ICD. And the only length information we have right now is CD is 3, CA is 3, and we know that CI is 8, and so AI is 5, and so AH will equal 5 times, or 5 over 8 times 3. And so we'll get 15 over 8. Right, any questions on that? So the main idea behind these kind of problems is obviously to figure out how to convert this into, or figure out how to convert the 2D picture into a 3D picture, right? And usually we assume that, what we assumed here was that the sphere was equally tangent in all, if you rotate it around the axis of symmetry of each of the cones, the sphere was equally tangent in all of the, so if we rotate around this axis and this axis, we would get the sphere, or by either of those two axes. And so what we assumed was that we only needed to examine this 2D cut, or this 2D slice of the whole picture. And so that's a valid assumption in this case only because it's symmetric about both these axes of symmetry. Alright. No questions, right? Okay. So, alright, okay. Anyway, so now if we, whoops, I think okay. So, there's a slight error here. So similar triangles are between, so this is why you should always write down what triangles, or how the triangles are similar here. So AIH is similar to triangle ICD. And so that's not exactly true. AIH is similar to IDC. And so AH equals to AI over ID times CD. And so AI equals 5. ID equals square root of 73. right? Because ID is equal to 8 squared plus 3 squared, and CD equals to 3. And so we can compute then AH equals 15 over root 73. Alright, so that's why you should always keep in mind how the triangles are similar. It's always best to write it out explicitly so you don't make mistakes like this. Okay, so now let's look at the next problem. So more circles. A flat board has a circular hole with the radius 1 and a circular hole with the radius 2, such that the distance between the two centers of the holes is 7. Two spheres with equal radii sit in the two holes, such that the spheres are tangent to each other. And we want to find the square of the radius of the spheres. So, obviously, we can attempt to draw somewhat of a 3D figure. Right, these are two holes, and then we got the spheres that sit in them, but it's usually hard to draw spheres. It's nearly impossible to draw spheres in any useful way. And so the best way to do sphere problems is to draw projections, or draw 2D slices. So the first 2D slice that we should probably draw is of the flat board. So if we look at the plane of the flat board, it looks something like this. So we have this length is 2, this length is 1, and this length is 4. Now the other 2D slice, so what other 2D slices could we draw? Well, it seems that everything is symmetric about this line, right? The line going through the centers of these two holes. So what if we draw, we draw the slice perpendicular to the plane of the flat board, but also going through this line, because everything will be symmetric about that slice. So if we draw that slice, the two spheres now turn into circles, and they're vertical circles, like that. And so the flat board is now a plane, or a line. And we have another sphere that looks something like that. And so, hold on, let me redraw this. So it looks more like, hold on, like that. And then the flat board is somewhere down there. And then this portion is like that. Okay. So this right here is a circle, this line. And so this circle corresponds to this circle right here. And so the length of this line is the diameter of the circle. And so the length of that line is 2. Now this line corresponds to this line. And so the length of that line must be 4. And this line corresponds to this circle. And so the length of this line must also be 4. Okay. So now, how do we go about solving this? So we have to first utilize the fact that the two circles are tangent. Right, so if we draw the centers, and as with any tangency problem, the first thing you should do is draw lines through the tangency points. And anytime you're present with chords in the circle, the first thing you should do is draw perpendiculars from the center to those chords. And we all know that these points are the midpoints of the chords. Okay, so now we have a couple lengths here. Let's length this 2r. This length in the middle is 7, right, from here to, from here to here is 7, and we know this is 2r. Now, do we know these lengths? Well, no, but can we figure them out? If we draw this point right here, this point is obviously r, or this length is r, and this length right here is 1. So what is this line right here? Square root of r squared minus 1, right, from Pythagorean theorem. If we do the same thing here, this is r, this is 2, and so this line is square root of r squared minus 4. And so now we have somewhat of a trapezoid in the center. So we're left with, this is 2r, this is square root of r squared minus 1, this is square root of r squared minus 4, and this is 7. So now a clear line to draw would be this line right here. And the reason for that being is we know this length, we know this length, and we know this length. And so now we can set up an equation for r using Pythagorean theorem on this new triangle that we just created. So the length of, or the triangle, zoomed in, would be 2r. This length down here is 7. This length right here is square root of r squared minus 1 minus square root of r squared minus 4. And so now we set up a Pythagorean theorem, because this is the equation r, obviously, and so we can solve. So we have 7 squared plus a large quantity squared, square root of r squared minus 1 plus square root of r squared minus 4 equals 2r whole squared. And so we have, let's see, 7 squared plus r squared minus 1 plus r squared minus 4 plus 2 square root of r squared minus 1 times r squared minus 4 equals 4r squared, and then we can finish this out. This goes to 2r squared, so this becomes 45, or square root of r squared minus 1 times r squared minus 4 equals to r squared minus 22. And so if we re-square both sides, so it's a general technique for solving these kinds of equations. R squared minus 1 times r squared minus 4 equals r to the 4th minus 44r squared plus 484. And so this gives us r to the 4th minus 5r squared plus 4 equals r to the 4th minus 44r squared plus 484. So this cancels, right? And then we're left with 39r squared equals 480. And so we r squared equals 480 over 39. And obviously this is not reduced, but we can reduce this easily. This comes out to be, yeah, so this is like 160 over 13. Right, so yeah, so the latex didn't quite come out right. It's just a bunch of typos for the M, but you guys get the idea, right? It should be a fraction. I'm sure you guys have seen enough AIME problems to where you understand that. Okay, so the main thing to observe from this problem is, first off, the fact that we had to use two views, right? Sometimes one 2D picture, and rarely does one 2D picture give you the whole picture of the problem. But if you use multiple 2D views in conjunction, you can figure out the problem. And so the idea behind these kind of tangency problems in both 2D and 3D geometry is to somehow write an equation in terms of r using Pythagorean theorem. 99% of the time you're going to be using Pythagorean theorem to write an equation in r. And so it's just a matter of finding which triangle to use, and which triangle to use, and and how to find the lengths of that triangle in terms of r, obviously. And so the problem here was to figure out, or to use the 2D, or use the 3D picture to figure out these lengths. Okay, alright, let's look at the next question. So a rectangular box has width 12 inches, length 16 inches, and height unknown. And so we're told that 3 faces of the box meet at a corner, and the center points of those faces are vertices of a triangle with an area of 30 square inches. Okay, as always, we start off with drawing a beautiful diagram. So we have a rectangle of unknown height, and so if we call this length is 12, this length is 16, and this length is h, which is what we're trying to find. The center points of these faces create a triangle whose area is 30. So what more do we know about this triangle? So area is 30, but we know that this length is 10, right? Because if we look at the 2D slice halfway through, the center here is the midpoint, that center is that midpoint. So this length is half of this length, which is 20, and so this length is 10. Right, because this is 16, this is 12. And so that length we know to be 10. So this is 10. And then what do we know about the other lengths? So if we do the same thing for each of the other lengths, So if we take a vertical slice, it looks like this, right? This length is 12, this length is h. Here, we should probably label these points. So we'll call this A, B, C. So this is C, this is B, this is A, and this is B. So what is the length of AB? Length of AB is square root of h squared plus 12 squared over 2. Or we could rewrite this as square root of h over 2 squared plus, actually let's leave it like that. So it's half square root of h squared plus 12 squared. So this is half square root of h squared plus 12 squared. And same with the other side, right? Obviously it's the same thing except with 16. So it's half square root of h squared plus 16 squared. Right. And we're told that the area of this triangle is 30. So we know all the side lengths, at least in terms of h, and we know the area. So what might be the most logical way to go from here? It'd probably be Heron's formula, right? So if we try applying Heron's formula, so we have A, B, C. This is half square root of h squared plus 12 squared. This is half square root of h squared plus 16 squared. And this is 10. So the semi-perimeter is, let's see, 5 plus 1/4 square root of h squared plus 12 squared plus 1/4 square root of h squared plus 16 squared. And so the area equals square root of this quantity times, right, we can apply Heron's formula, but this looks like it's going to be a lot of work. So what might be a much easier way of doing it? So one way we can do this is we know the area, right? And so the only reason we applied Heron's formula is because we knew all the sides. But where might we go with the area if we know a single side? So we know that this is 10. So from there we can conclude that the height right here is 6, right? And so now if we apply Pythagorean theorem here, then this, so if we call this AD, BD equals h over 2, right? It equals, that's because, so it equals half square root of h squared plus 12 squared squared minus 6 squared square root, which comes out to be, if we do the algebra, it comes out to be h over 2. So BD is h over 2. And what about AC, or CD? So CD equals, right, the same thing. And this one is not as simple. Half square root of h squared plus 16 squared minus 6 squared. And so this comes out to be square root of, or half square root of, so this is squared. So this is half the square root of h squared plus 112, right? And so now we know BD, we know CD, and so easier way to do this might be we take BD plus CD equals 10, and so now we plug in h over 2 plus half h squared, or half square root of h squared plus 112 equals to 10. And this is a simple equation that we can all solve, right? And so, interesting. So one of you guys suggested Desguas' theorem, and that's a possibility. We could apply that. But every geometry problem on AIME can be done without the use of any advanced theorems. Just adding a couple lines and using a little ingenuity should be able to solve every problem. So while it helps to know these kind of advanced theorems or more obscure theorems, they're not necessarily useful, and they could distract you from the more simpler method of doing the problem. Okay, so let's look at the next problem. So in triangle ABC, BC equals 23, AC equals 27, and AB is 30. Points V and W are on these, right? And then, so the key things to notice are, first off, there's the table is level, right? So that means the height is the same from all three triangles. And so essentially we want to find the maximum possible height. So this looks like a case of, well, first off, the 3D part of this is simply noticing that the height from each of the vertices is the same. So the way they draw it here, we have a hexagon, and since it's placed on a level floor, right, these heights are the same. So this is A, or I guess this is A is back here, B and C, and we call this height HA, this height HB, and this height HC. All these heights must be the same for it to be level, so we'll just call this common height H. So now if we go back to the 2D picture, which they've conveniently drawn for us, okay. So the first thing to notice is there's a bunch of parallel lines, and that immediately makes me think, okay, similar triangles, because AC is parallel to, and there's some weird labeling of points, U, V, W, X, Y, and Z. And so since all three of these, U, V, W, X, and Y, Z, are parallel to the sides of the triangle, there's definitely similar triangles involved. So we know that this is H, this is H, and this is H. And so we know that the sides of the triangle are something like 23, 27, and 30. So this is 23, 27, 27, and 30. Okay. So what's the limit here? Well, how do we get to a maximum? Let's first figure that out. So this UV can potentially move further down, and then WX will have to move further down, right, because the heights must be the same, and then so will YZ. And so eventually, at some point, V and W are going to meet, and they're going to be the exact same point. Or U and Z will be the exact same point. Or Y and X will be the exact same point. So what's the limit here then? Which of these could it be? So if we just analyze this first, what is this length right here? AV. How do we figure out that length? Well, in terms of H, obviously, right, we're trying to maximize H. So if we let now the height from A be HA, height from C be HC, and the height from B be the same thing, then the ratio of similarity of each of these triangles is obviously H over HA, H over HB, and H over HC. So what is then AV? AV equals to H over HA times AC, which is 27. And then we also have, if V and W are going to meet, we have WC equals H over HC times 27. And the criteria is AV plus WC must be at most AC. Right? We can't have them overlap, otherwise the table is non-existent. So if we now plug in our formulas, 27 plus H over HC times 27 is at most 27. Wow, how convenient. And so if all these cancel, and we rearrange, we get H is at most, let's see, HA times HC over HA plus HC. And so, we have found a bound for H, a maximum bound. Now, if we apply these for the other three sides, or the other two sides, BC and AB, then we get similar things, right? We should get H is at most HA times HB over HA plus HB, and H is at most HB times HC over HB plus HC. And so we found three different upper bounds for H, and so all that remains now is to compute them and figure out which one is the smallest, because that's obviously going to be the maximum H can be. And so how do we go about computing these? Well, we need to know HA, HB, and HC. So how do we figure that out? The only thing we're given are the three sides of the triangle. So to get the heights, we need to get the area first. And to get the area, since we're given the three sides, the most sensible way would be to use Heron's formula. So if we use Heron's formula, right, S equals 35, and so our S equals 40, and so area equals square root of 40 times 17 times 13 times 10, and so this comes out to be 20 square root of 17 times 13. And notice that you probably noticed this in like probably many past problems, but I don't simplify I don't usually simplify numbers. I leave them as products or squares until the end, because it makes computation a lot easier, and it makes it a lot easier to notice a lot of common factors and a lot of factors that you might miss when you're trying to simplify fractions or radicals. It's much easier to see that 17 times 13 is 17 times 13 than if it was written as like 221. It would be much harder to see that 221 equals 17 times 13. And so now that we have area, we can figure out HA, right? It equals to 2 area over 23. HB equals to 2 area over 20 or 30. And HC equals to 2 times area over 27. And so now that we have this computed, we can then compute each of these upper bounds and figure out which one is smallest. And once we know which one is smallest, we've computed the maximum possible value of the height. Alright, are there any questions? So the maximum time for this class to end is 5:30, but if we finish early, then you guys can leave early. Alright, anyways, so let's move on. Okay, so problem 6 is a cylindrical barrel with radius 4 feet and height 10 feet is full of water. A solid cube with side length 8 feet is set into the barrel so that the diagonal of the cube is vertical. And then it's implied that the cube will fall until it rests on this on the top surface of the barrel. And we're trying to find what volume of water is displaced, meaning what volume of water that was inside the cylinder is now occupied by the cube. As always, we draw a good diagram. But thankfully, they've drawn the diagram for us. And so, let's see what we can dissect from it. So first thing is the diagonal of the cube is vertical, meaning that all three sides are symmetric. It's symmetric about all three sides. And so if you notice, they've drawn three sides that are going to be resting on top of the barrel. And since those three sides are going to be resting on top of the barrel, there's going to be 3 points where the cube touches the top of the barrel. So if we look at the top of the barrel, it's a circle, right? And there's 3 points that touch. And since all these 3 points are symmetric about the center, notice that because the diagonal of the cube is vertical, it's not too far to assume that the diagonal of the cube is on top of, or the diagonal of the cube is directly through the center of the cylinder. And so this point right here must obviously be the diagonal of the cube. since we're looking at a projection, and so it makes sense that these 3 points form an equilateral triangle simply because they're symmetric. So we have to exploit the symmetry. Exploiting the symmetry is a key technique. So let's use the fact that this is an equilateral triangle. Okay, so what else can we dissect? Now if we look at the cube, right, and we assume that this edge, or this point, is the one that's submerged, then this equilateral triangle corresponds to an equilateral triangle that looks something like this. And so the volume of water displaced is going to be the volume of this solid right here. If you notice, it's a pyramid with an equilateral triangle as a base, but it's also a tetrahedron, meaning it's a pyramid in 3 different ways. And so we can now go about computing this. So first things first, what do we need to know to compute the volume of this tetrahedron? Well, the easiest way to compute the volume of this tetrahedron would be to notice that, okay, we need a height, always in 3D, the easiest way to get the volume is going to be a height and a base. Our height and base area. So we can figure out this the equilateral triangle base area, right? Assuming we do some geometry and figure it out. But how do we figure out the height from this vertex to the equilateral triangle? So there doesn't look like a simple way to do that, although it's theoretically possible. We could figure out where the centroid of this. So when we drop the altitude from this vertex, it's going to land on the centroid of the triangle, right? And so if we draw, so here I will zoom in. So that tetrahedron looks something like this. And so when we drop the height, it's going to land on the centroid of the triangle. And so if we draw this line right here, drop the perpendicular from the centroid to a side, and we draw this line right here, we will end up with a right triangle. And so given the side lengths of this equilateral triangle, if we figure out the side lengths, then we can figure out this length right here, right? Here. This length right here. Here, I should probably label this. So A, B, C, D. So B, C, and D. And so given BC is S, then AB equals S over root 2, right? Since this is all symmetric. And so since we have A, B, C, D, we'll call this centroid G. And so we have AG, and we'll call this midpoint M. And so we can figure out that, okay, AM is going to be S over 2. GM is going to be S root 3 over 6. And so we can figure out AG based in terms of S. And so we can calculate that AG comes out to be, let's see, AG will be S squared over 4 minus square root of, so AG equals square root of S squared over 4 minus S squared over 12. And so this comes out to be S squared, or S squared over 6 square root. And so this will be S over root 6. And so AG comes out to be S over root 6. We know the area of triangle BCD is S squared root 3 over 4. And so the volume equals to 1/3 times S squared root 3 over 4 times S over root 6. And so this comes out to be, okay, yeah, and so this comes out to be S cubed, so S cubed over 12 root 2. And so that's what we wanted. However, there's a far easier way to figure out the area, or the volume. So if we notice, we were looking for a height and a base, right? The height and the base are almost given to us because of the fact that this lies at the end of a cube. So last time we chose base to be triangle BCD, and so the height would be from vertex A. But what if we choose the base to be triangle BAD instead? So if the base is triangle BAD, then the height is AC, and so the area of the base is the area of triangle BAD, which we've already figured out is S over root 2 times S over root 2 over 2. And so this comes out to be S over 4, or S squared over 4, is the base area. And then the height is length AC, which is S over root 2. And so the volume is S squared over 4, or 1/3 S squared over 4, times S over root 2. And so this is S cubed over 12 root 2. Notice how this method is far easier than the previous method. Okay, so now let's see. Now we know that it's S cubed over 12 root 2. All that remains is to find S. So if we remember, right, S was the side length of equilateral triangle. Now notice how the height of the cylinder nor the side length of the cube matter in this case. Only the radius of this circle right here matters. So the radius of this circle is, we're told it's 4. And so if the radius is 4, if we drop the perpendicular here, this angle is 30. And so this length right here is 2 root 2, or 2 root 3. And so S equals 4 root 3. And so it's pretty easy to then compute. S, or V equals to, 64 times 3 root 3 over 12 root 2. And so this comes out to be 16, or 8 root 6. Alright, any questions on that? So notice how we had two methods of computing the volume. The first method was far more computation and many more places to make errors than the second method, which was simple because we chose a different choice of base and height. So it's the idea behind these geometry problems is generally to draw lines or to choose a way of doing it that makes the computation far easier. So generally geometry problems, you shouldn't have like 3 pages of computation. It should be within half a page, if not less. All right, and if it's taking a ton of computation, you obviously know that there's a better way to do it, or that you did it wrong. Okay, so let's look at the second problem. So cube ABCDEFGH is labeled as right, and then it has edge length 1, and it's cut by a plane passing through vertex D, and midpoints M and N. Okay, and so the plane divides the cube into 2 solids. The volume of the 2 larger solids. Okay, so essentially we're trying to find the volume of the larger of the 2 solids. So as with all geometry problems, we start by drawing a diagram. Though in this case the diagram is given for us. But it's always a good idea to just redraw it on your paper, because redrawing the diagram can help you see things that you might not have seen if you're just staring at it. So this is D, this is A, B, C, D, E, F, G, and H. And so this right here is midpoint M, and this right here is midpoint N. And so, so this is the triangle DMN, and so the plane that cuts through that triangle cuts this cube into 2 different solids. Okay, so obviously this triangle is not if we take the cross-section of the plane that's inside the cube, this triangle is obviously not the cross-section, right? So, hold on. Okay, so the triangular cross-section is triangle DMN. But is it? There's an extra cross-section that we're not considering. And that's because if you extend triangle DMN, or the plane of triangle DMN, it intersects side FB at some point we'll call, say, X. So where exactly does it intersect side FB? Well, that's equivalent to finding the length XB, right? So we want to figure out XB. So let's so that's one part of the problem. But even if we figure out XB, where do we go from there? We want to figure out the volume of this large solid, and so it might even be easier to complementary count or compute the volume of the remaining solid, right? So we want to find the volume of the smaller solid. But obviously, it's not some sort of a regular solid, right? It's like dmxb cn or dmncbx, and so this is a complex solid. So how might we split it to figure out its volume? Obviously, when we're presented with some sort of weird solid like this, the idea behind finding its volume, or even its surface area, is going to be splitting up the solid into a bunch of different pieces that are representative of regular solids that we know, like pyramids, rectangular prisms, tetrahedrons, so on. So how do we split this up in such a way that it's easy to compute its volume? So if we draw, say, line DB, and we look at and line DX, so line DB and DX, then triangle or tetrahedron DMXB is a tetrahedron, and DNCBX is a pyramid with the vertex D and base NXBC. And so the reason I chose these two specific solids is because it's easy to compute the volume of these, since the volume of DMXB, so volume of DMXB equals the height of DMXB is simply XB, and the base is DMB, right? Because since XB is perpendicular to triangle DMB, and so, okay, so the volume of this is going to be 1/3 XB times the area of triangle DMB. And what's the area of triangle DMB? Well, we know we can figure out the length of DM, right? AD is 1, AM is half, and MB is half. So the area of triangle DMB is simply equal to the height, which is AD, times the base, which is MB, over 2. And so the area of triangle DMB is simply 1/4. And so if we find XB, we can find this. And so this is easy to find. Now what about the other piece of the solid, which is the pyramid DXNCB? CB. Well, since it's a pyramid, its volume is going to be 1/3 base area times height. And so the easiest way, the height in this case is fixed because it's a quadrilateral pyramid. It's not a triangular pyramid, so it's not a tetrahedron. And so because of this, the height is fixed. It must be the height from D. So the height from D is easy to compute because it's just DC. And DC we know is 1 times the area of quadrilateral NXBC. Now, quadrilateral NXBC is a trapezoid with 2 right angles, right? And so its area is going to be NC plus XB over 2 times its height, which is BC. And now we just plug in the lengths we know. DC is 1, BC is 1, NC is half. And so, assuming we know XB, we can quickly and easily compute that the volume of the entire, or the volume of the smaller solid is, let's see, this comes out to be 1/12 XB, which let's call XBH. So this is 1/12 H, and this is 1/6 H plus 1/12. And so the total volume is then 1/4 H plus 1/12. And so the volume of the larger solid, which is our answer, which we're trying to find, is, so this is V prime, is equal to 11/12 minus 1/4 h. So all we need to do now is compute h. So if we try to compute h now, let's see. Now let's see if we can compute h. Okay. So when we're dealing with planes, the main idea behind these planes, so I'm going to leave out the point names, because I'm sure you guys remember the names from the previous slide, but dx, m, and n all lie in the exact same plane, right? They're coplanar points. And so we can utilize, usually when we're trying to figure out the location of x, we want to utilize similar triangles. So if I draw dx and mn, they intersect at some point we'll call q. And so what we're trying to find is xb. So what's the similar triangle analog of xb? Well, that would be qb, right? qb. And so if we draw then so it would be q, this point down here that we'll call, let's see we'll call this h, we'll call this k. So qk is perpendicular to this bottom face, and so is xb. So triangle, if we look at triangle DXB, QK lies somewhere along there. And then if we look at draw M, let's see, C, and we look at triangle, if we then look at triangle, let's see, M and C, then Q lies somewhere right here. And when you drop Q down, we get K. Okay, so we have two perpendicular cross sections. So how do we figure out, or where do we go about figuring this out? Well, first thing to notice is K. K is simply the projection of Q onto the bottom face, which is A, B, C, D. Right? K is simply the projection of Q onto A, B, C, D. And so the location of K would be determined by the line, or the projection of the line dx onto A, B, C, D. And so the projection of the line dx onto plane A, B, C, D, so this is obviously M, right here. So the projection of that line would simply be line DB, and the projection of point N onto this face would just be point C. And so this is the projection of N, and so this point right here is K. So we know a lot of things here, first off. We know, or we can figure out pretty easily, that we can figure out the location of DK simply because this is 1, half, half, 1, and 1. And so this length, MK, or triangle DKC and triangle MKB are similar. Because, yes, I'm okay. Thank you for your concern, though. Right, so these triangles are similar because these angles are equal. And so because these triangles are similar, the ratio of similarity is DC to MB, which is 1 to 2. And so DK is going to be 2/3 of DB, which is √2. So this length right here is 2 √2 over 3. And this length right here is √2 over 3. And then CK is going to be 2/3 of CM. And CM we can figure out as √5 over 2. And so this is going to be √5 over 3. And KM is going to be √5 over 6. So now we can plug in what we have. So MK is √5 over 6. This is √5 over 3. We know NC to be half. And we can figure out MN, right? we can figure out QK. And QK comes out to be, let's see, 1 over 6. Right? And so QK, we now know to be 1/6. And we know that DK is 2 over 3. We know DB is root 2 over 3. And so we can figure out now from similar triangles that XB is then 1 over 4. And so XB we figured out as 1 over 4. So we go back and plug it in here. We get V equals to 11/12 minus 1/16. And we can compute that pretty easily. Alright, so any questions on how to use similar triangles to figure out the projection of a plane onto a line? So now you guys should be able to apply this kind of technique if, say, we take, if we have a cube, and instead of a vertex and 2 midpoints, we take, like 2 vertices and a midpoint. Right, 2 vertices and a midpoint. Then where's the projection of this plane on all the other lines? And you guys should be able to figure that out now. It's a simple expansion of this. It's a simple expansion of this technique right here. Alright, so now let's look at the next problem. So a cube with side length 10 is suspended above. So these last 4 problems are significantly more difficult than the previous 7. So the cube with side length 10 is suspended above a plane. The vertex closest to the plane is labeled A, and the 3 vertices adjacent to vertex A are at heights 10, 11, and 12 above the plane. The distance from vertex A to the plane is what? Okay, so if we have a plane like this, right, and then a cube is suspended such that there we go. This is hard to draw, but something like that, right? I won't draw the rest of the cube, but you get the idea. So this is vertex A. We know this distance is 10, this distance is 11, and this distance is 12. What nice numbers. 10, 11, 12. Consecutive integers. And what we want to figure out is, what is this distance? Wow, so, this problem looks completely impossible, at least just the way it's drawn right now, because there's so many different variables to figure it out. Right, we have, first off, we have the side length of the cube, which we'll call, say, S. Oh, never mind, they gave us the side length. Side length is 10. There's just a bunch of different variables here. So, an easy way to do this would be if we. So this is the main idea behind this problem is how do we get started on this? The way it's drawn, there seems to be no simple jumping point into the problem, but there's a quick transformation we can make to make this problem far, far easier than the way it's drawn. So if I now impose a coordinate plane on this, a 3D coordinate plane, and we place A at the origin, B, C, and D. We place A at the origin. We place B along the x-axis. So B is 10, 0, 0. C along the y-axis. 0, 10, 0. And D along the z-axis. 0, 0, 10. Now, why would we do that? What's the motivation behind that? Well, first off, a coordinate system simply makes sense because we're dealing with a cube, and so cubes fit amazingly on coordinate systems. And we're dealing with cubes and undefined planes, and so the reason we would want to switch to a coordinate system is A, because it's easy to write the distance. There's a simple formula for the distance from a point to a plane. And B, because cubes fit so perfectly onto a coordinate plane. And it just makes sense to choose A as the origin, B, C, and D as these 3 points. So now let's see what we can do with this. Well, if we rewrite this, or if we impose a coordinate plane on this, then this plane has an equation. The general equation of a plane is ax plus by plus cd or cz plus d equals 0. And well, you can always scale up the plane, but if we scale it down or normalize it, and we use the condition that a squared plus b squared plus c squared must equal 1. So we're using this condition to normalize the plane, or the equation of the plane. And so this is a unique equation for the plane. There's only a singular equation that satisfies these two constraints for any given plane. So now let's go about using the distance. So I'm not sure how many of you guys know this, but the distance from a point alpha, beta, gamma. The distance from a point alpha, beta, gamma, with coordinates alpha, beta, gamma, to the plane that we defined on the previous slide is given by this formula right here, which is a alpha plus b beta plus c gamma plus d over square root of a squared plus b squared plus c squared. And so the derivation behind this is not that hard, but it takes a little time, and so I won't go into that. But take this for granted. This is the distance from a point to a plane, and so the easiest way to think of this is you simply plug in the point into the equation of the plane, and then divide by square root of a squared plus b squared plus c squared. And this is simple. This is similar to the distance from a point to a line in 2D geometry, right? In point to a line, you just don't have the d variable, and you don't have cz. It's just c. And so the way we define the plane was that the bottom is equal to 1, and so this is a alpha plus b beta plus c plus d. Okay. Now we're told that the distance from points B, we're told the distance from points B, C, and D, and so sorry, I have a cold today, but anyways, so we're told the points distance from points B, C, and D. So from point B, the distance is, if we plug in alpha, beta, gamma equals 10, 0, 0. So from point B, the distance is 10 alpha, or 10a plus d. From point C, the distance is 10b plus d. And from point D, the distance is 10c plus d. And so what we end up with is 10a plus d equals 10a plus d equals 11, or 10. 10b plus d equals 11. 10c plus d equals 12. And so this looks like we have 3 equations and 4 variables. So what do we do here? Well, we have to not forget, we also have the additional constraint that we imposed at the start, which was a squared plus b squared plus c squared equals 1. Or we can just get rid of the square root. So this is the additional constraint that we imposed. And so now we have 4 equations, 4 variables, and so this should be pretty easy to solve. And so we can see a equals to 10 minus d over 10, b equals to 10 minus d over 11, c equals to 10 minus d over 12, and so it might be, or what the, so this is 10 minus d over 10, 11 minus d over 10, and 12 minus d over 10. And so we know ABC. In terms of d, we can plug it in here and solve for d, right? We all know how to do that. It's just a quadratic equation. And so we can get the value of d. Alright, so now that we know d, or we can figure it out, just compute it, how do we use that? Well, what we're trying to find is the distance from A to this plane. So the distance from A to this plane is simply going to be, if we plug in alpha, beta, gamma equals 0, right here, for A, it's just going to be d. And so what we're really trying to compute is just d. So once we compute d, that's our answer. Alright, any questions? So the main idea, the reason this question was so hard is because it's impossible to approach this question without using that method. If you don't use that method, I don't know how you approach it, but it's simply just non-approachable. And so that's what made this question a little hard, was to think of that tricky method. Alright, so let's move on. Question 9. Alright, anyway, so question 9. Equilateral triangle ABC has side length 600. Points P and Q lie outside the plane of triangle ABC and are on opposite sides of the plane. Furthermore, PA equals PB equals PC, and QA equals QB equals QC, and the planes form a dihedral angle. So there's a point whose distance from A, B, C, P, and Q is D, and we want to find that distance D. So first off, a lot of symmetry. A, B, C. As always, start off with drawing a good diagram. That's the first step in any geometry problem. If you don't draw a good diagram, you can't solve the problem. Alright, anyway, so P is somewhere up here. And we have the constraint that PA equals PB equals PC. And Q is down here with the same constraint. Right? So what does that tell us about P and Q? If we drop the altitude from P, anyway, so if we drop the altitude from P, right, let's see. If we drop the altitude from P, wow, so it's hard to see, it's kind of hard to see where all these lines are, which is why it's beneficial to draw dotted lines, because now that I'm looking at it, it's kind of confusing to see which lines are in the front and which lines are in the back, right? So anyways, we have P, and so if we drop the altitude from P, ABC is an equilateral triangle, right? So it has a centroid, and so obviously dropping the altitude from P is going to land right on the centroid, right? It should be landing right in the center of the triangle. And same with Q. Because QA equals QB equals QC, and because PA equals PB equals PC, the two should meet at the centroid. And so PQ, the line PQ, passes through the centroid of the triangle. And so, obviously, point O should also lie on that line, because point O is equidistant from A, B, and C, and so point O should lie on line PQ. And because OP equals OQ, O should be the midpoint of PQ. Okay, so what can we do with that information? So the only other thing we're given is that QAB form a 120 degrees dihedral angle. So what can we do with that? Let's see. So we don't know that we don't know where points P and Q are, how far above they are, or how far below they are. We also don't know. Okay, so obviously this is defined only because of the existence of O, but we could claim, okay, so the positions of P and Q are not fixed. So what if P and Q are equidistant above and below? And so O would simply be the circumcenter of ABC. And so we can quickly compute that, right? But that's not necessarily true. And I'll leave that to you guys to figure out why not. But there's a hidden subtlety in there making that not true. So obviously this is a defined configuration given the existence of point O. But how exactly do we figure that point out? Well, it might be easy to let the height from P be x and the height from Q be y. And then the distance d is obviously x plus y over 2, right? And so, first things first, if O lies somewhere below the plane, right, we'll assume y is greater than x, O lies somewhere below the plane, and we draw this triangle right here, OB, and we'll call this circumcenter as G. So if we draw this triangle OBG, and the reason I'm drawing this is because we know the length OB, we know the length BG, and we know the length GO. OB we know is D, and D we know is x plus y over 2. GO we know is x minus y over 2, or y minus x over 2. And we know that BG is equal to, well, this is easy to compute, but it comes out to be 600 root 3 over 3. And we'll replace 600 with s here. So this comes out to be s over root 3. And so we have we have a Pythagorean theorem equation, and we know s, so that we can write in terms of x and y. So we have x plus y over 2 squared plus y minus x over 2 squared equals s squared over 3. Alright, so pretty simple. But we have two equations, or two variables, one equation. So what do we do with this? We obviously need one more equation, and we haven't used we haven't used this thing in the problem of the 120-degree dihedral angle. So how do we use that? Well, if you remember dihedral angle, right, we drop a perpendicular from P to AB, drop a perpendicular from Q to AB, and they should both obviously meet at the same point, which we'll call M. And so if we draw a triangle PQM down here, we have P, we have Q, we have M, and remember that perpendicular to M should obviously be G. And so G, we can figure out, comes out to be S over 2 root 3. That's well known, right? MG comes out to be S over 2 root 3. We know that this angle is 120 degrees. And we know that this is X and this is Y. So how do we convert angle information to length information? What does angles and lengths together make you think of? What strategy? What might we apply? Angles and lengths. It obviously makes us think of trig, right? And so, since we know that the two legs of each of these two right triangles. So if we want to apply trig, which trig function might we use? Tan. And so if we're going to use tan, right, the most obvious equation in this case would be tan of 120 equals to tan of these two smaller angles. So angle QMG, and angle PMG. Right? And so we know tan of QMG is x over s over 2 root 3. And tan of PMG, or QMG, is y over s over 2 root 3, sorry. And tan of PMG is x over s over 2 root 3. And tan of 120 is negative root 3. And so we have our second equation in terms of x and y. And so now we have two equations, two variables, and so we should be able to solve. Alright? So any questions on this? So this is a kind of a more complex problem. But the motivation, I hope I explained the motivation clear enough behind this solution and why we would think of this solution specifically. If you have any questions, feel free to ask. Okay. Well, if not, then let us move on. So problem 10. So it's a notorious problem. A block of wood has the shape of a right circular cylinder with radius 6 and height 8, and its entire surface has been painted blue. Points A and B are chosen on the edges of one of the circular faces of the cylinder, so that AB on that face measures 120. And we slice the block in half, and we want to find the surface area of this weird, non-geometric figure. So, wow, this is hard to draw too. So like that, and obviously we might conclude that, okay, this looks like a circle, a rectangle, or whatever. But if you look a little closer, this looks nothing, that's not a circle, nor is it a rectangle. Then our second idea might be, okay, so this curve, let's call these points up here C and D. So A, B, C, and D, or A, B, C, D, that face looks something like this. A, B, C, D. So our next thought might be, okay, let's split this into circle sectors and straight line sectors. So obviously CB is going to be part of a circle sector, AD is going to be part of a circle sector, and we can try that, right? That's a valid strategy. That makes sense based on our experience. Whenever we're trying to find the area of these kind of curved and straight line sections, split it up into circular sectors and triangular and rectangular sectors. And so we can try that. That's a valid strategy. But I'll save you guys the time of trying that and tell you that it doesn't work. So we can't split this up into simple circular sectors and triangular sectors. So now we're stuck. What do we do? So this problem requires a little bit of ingenuity, only because you have to see a simple way of calculating this area, since we can't split it up into sectors. So the simplest way, and this is not trivial by any means, but would be what happens if we drop C and D, and we call this C prime, D prime. So AB, if I look at AB, C prime, D prime, it looks something like this, right? AB, C prime, D prime, and we notice that if I'm looking at the parallels between these two, this is equal, except for this distance are different, right? So the key thing to notice here is that if I take A, B, C prime, D prime, and we stretch it, we simply stretch it in this direction, we end up with A, B, C, D. And so, alright, anyway, so, so if we stretch it, we end up with A, B, C, D. That's the key thing to notice here, is that we can take A, B, C, D prime, and stretch it along the line AD or BD, or AD prime or BC prime, and we end up with this geometric figure right here. And so it's easy to calculate the area of ABCD prime, right? It's a bunch of 120-degree sectors. ABCD prime is, if we draw in the circle around it, they're both 120-degree sectors. And so we can split this up into two sectors of 60, 60, and these triangles are 120, 120. And so the radius, we're told, is something like, it's 6. So this is 6, this is 6. So we can calculate the area of this sector, right? So we can calculate AB, C prime, D prime. And so to calculate the area of this, now all we need is the scaling factor. So we just need the length AD to AD prime. Or another way we might figure it out is, if I look at the centers, right? The center of this figure 1, we'll call this in figure, center of figure 1 is just the center of the circle. And I draw the perpendicular to chord AB. Let's call this E, or the center we'll call O, and this midpoint we'll call M. And so OM equals, that's easy to figure out, that comes out to be 3. And then OM is 3, right? And so if I go halfway up to the center of this figure 2, which we'll call O prime M is something that would give us the, if we know O prime M, that would give us the scaling factor, right? And so if I look at the triangle, O prime, O, M, O prime, O, M, we know O, M is 3, and O prime O is just half the height, right? Because it's just halfway up. So this is 4, this is 5, and so the scaling factor is simply 5 over 3. And so once we know the area of ABC prime D prime, multiply by 5/3, and that gives us the area of ABCD. Alright? And so there's one more problem left. I encourage you to, so that's all for today. We ran out of time. But there's one more problem left. And so this final problem is unique because there's a very simple way of doing it. It should require exactly one line to do it. But to get there, to think of the way to do it is the hard part, obviously. And so I encourage you guys to try it. Hopefully these last 2 or 3 problems, you realize that when it comes to geometry, It's more about the geometric part compared to, rather than the computational part. So I'm sure you guys have heard of like chord bashing and trig bashing, but bashing is not the way to go about geometry problems. If there's one thing you learned today, it should be that bashing is not how you deal with geometry problems. There's always a much more simpler and elegant way. Alright, so that's all for today, and I will see you guys next week. Hopefully I won't have a cold next week. But thank you. Go Dumbo.